Today we are going to be talking about active versus passive control systems. So passive systems are systems that do not use sensors or rely on external power in order to adapt to the environment they are in. Instead, they rely on mechanical parts to change their behavior. If we were to build a robot that used a passive control system to keep itself moving in a straight line, we would make sure the servos were finely tuned to move at the same speed. We would make sure the wheels had large coefficients of friction so that they would not slip during motion and a straight path could be achieved. Active control systems are systems that do use sensors and may rely on external power in order to adapt to their environment and control their behavior. If we were to build a robot that used an active system for control, it would have sensors to detect motion, or if we were following a taped line, it might have color detectors so that the robot would know it was veering off, and it could adjust the speed of the servos automatically to keep itself moving straight. One place that passive control systems are used in the real world is in the construction of buildings and bridges. When strong winds or earthquakes occur near structures, their vibrations that result can be destructive to the structure and cause it to collapse or become damaged. One way to help the buildings adapt to these environmental changes is to include materials with high energy dampening properties in the construction of these structures, such as rubber, in order to dampen vibrations. Another method used for control is what's called a tuned mass dampener, or TMD. A TMD is a specially designed device that uses a pendulum to dampen vibrations caused to structures by removing kinetic energy from the structure and transferring it to the swinging mass of the pendulum. TMDs must be tuned specifically for the structures they are going in by adjusting properties of the pendulum such as mass or length. Continuing with the example of bridges and structures, many of them, instead of relying on the passive systems involving the material structure or mechanical dampening devices, use active systems instead, which have sensors that detect the force applied to the structures and electrical machines that can apply an opposite force to maintain an equilibrium. An example of one such device that is often in active systems is called active tendons. Active tendons are essentially linear actuators attached to the bases of support cables on bridges and structures that can either tighten or create more shock in the cables in order to balance out any applied force to the structure.
Passive systems are generally much more simple and cost-effective than their active counterpart, as they do not require the use of sensors or energy supplies. This makes them a better choice in accomplishing basic tasks such as dampening. Also, due to the lack of moving parts involved in a passive system, there is a greater stability and insurance that the system will perform as expected. Otherwise, the passive system may not have a broad range of actions to employ, as it only has a basic response that cannot be controlled by external supplies. This means that not only can it perform few tasks, but cannot be extended much further beyond its current performance. Whereas active systems have many areas of unexplored capability and can perform much more than passive systems. Still, this requires more moving parts and external power, which also includes a greater risk of failure. Active systems may be more necessary in the implementation of complex tasks that require multiple responses and nuanced logic. Because a passive system in a robot would require the mechanical design of the robot itself to be able to follow a line rather than a response from sensors controlled by an external source of energy, a passive system would not be effective in following a line. Active systems, on the other hand, can employ many methods to follow a line. A basic outline of one such active system would involve using a color sensor on a moving robot that could detect where the line is and be able to adjust direction to keep the line centered in its motion. Because a passive system has no external power to enable its action, the control force acts according to the excitation. Returning to the real-world examples, the dampening method of a tuned mass damper has a control force that comes from the vibrations that cause the building to move. When an earthquake occurs, it excites the building by causing an oscillation of the building, and the response of the damper is powered by the building's oscillation. In an active system, the excitation of an earthquake not only causes the building to shake, but triggers sensors that activate a response, such as the powering of active tendons to tighten its cables to prevent motion. This response to the earthquake is the feed forward. The feed backward is caused by the response to the initial action. As the building's motion responds to the tightening of the tendons, Sensors detect a shift caused by the tendons to decide whether to continue tightening the cables or loosen its tension.